Good day. This project is located at Corlette Drive in Johannesburg and forms part of a commercial fast food retail development. MyTech nominated the project in the light steel frame roofing category, focusing on the roof structure as the primary engineered element. This brand's flagship developments are no longer treated as standard fast food buildings. Globally and locally, flagship stores are used to express brand identity through architecture, requiring cleaner roof lines, greater spatial clarity, and higher levels of construction precision than traditional rollout formats. The Corlette Drive project sits firmly within this context. The brief demanded a structure that could support a contemporary architectural expression while remaining efficient, repeatable, and operationally robust. This placed particular emphasis on the roof as a defining architectural element, where structural performance and visual refinement had to be resolved together. I am Nesh, Commercial Director for MyTech, and I am presenting this project on behalf of the professional team for the Corlette Drive development. The professional team were Impendulo Architects, MGD Consulting Engineers, and Top Hat Roofing. The architectural brief was to create a flagship style fast food outlet with a floating roof expression. The roof was the dominant feature, requiring long spans, deep overhangs, and curved edges, while keeping the structure visually light and free of internal columns. This intent directly shaped the engineering approach. It demonstrates how contemporary commercial architecture increasingly relies on close alignment between design intent and structural strategy. Johannesburg is a climate with large daily temperature swings, high UV exposure, seasonal summer rainfall with wind uplift, and all of these conditions placed emphasis on the roof design. Roof durability and long-term performance, resistance to cyclic thermal expansion movement, wind uplift control, and detailing accuracy became major factors. Steel enabled the creation of long-span roof structures and extended cantilevers that were essential to achieving the floating roof aesthetic. The ultraspan light frame steel system provided the structural flexibility required to accommodate curved roof geometry and varying cantilever lengths with high precision steel. Steel allowed the architectural form to be resolved structurally without compromising buildability or accuracy. The ultraspan roof system enabled large open internal spaces, supporting efficient customer flow and operational layouts, typical of a high-volume takeaway facility. This particular fast food brand has been at the forefront of adopting industrial light steel frame building systems in South Africa. Their first light steel frame building outlet opened in Goodwood, Cape Town in 2013. According to SA Franchise Brands, this approach delivered significant efficiencies, a 30% reduction in material waste, 80% fewer transport loads, and a carbon footprint notably lower than conventional methods. And this has become the footprint that this flagship brand wants to roll out. Prefabricated steel components from the ultraspan system allowed for controlled fabrication, ease of transport, and efficient site assembly, even with the long span elements. The structural system accommodated a non-standard inward-sloping roof design, incorporating a concealed box gutter solution to manage internal drainage while maintaining clean external roof edges. Quoting again from SA Franchise Brands, the light steel frame building systems also offer improved thermal performance, cooling faster and warming quicker than traditional masonry-based structures. The roof component in ultraspan as part of the roof solution added to the value of the improved thermal performance of the overall building structure. This is a commercial retail building, but the roof solution is far from typical. Ultraspan was selected to achieve long spans with minimal material, while accommodating cantilevered eaves and a concealed drainage strategy. A key technical requirement was that the roof falls inward towards the external walls, necessitating the box gutted design and maintaining a clean roof edge. This required precise coordination between structure, drainage, and finishes. The total cost of the Corlette Drive project was 40 million rand, and it was completed at the end of March 2025. It is in the sector of the quick service restaurant food retail facility. Corlette Drive demonstrates how a carefully engineered steel roof system can elevate a conventional commercial retail building into a technically sophisticated and architecturally distinctive solution. The primary roof truss spanned 18.6 meters in total length, incorporating cantilevered eaves of 4 meters on either side, and a clear span of 11.6 meters, delivering the required architectural form with minimal material usage. This project challenged convention through the introduction of a floating roof expression, incorporating long spans, deep cantilevered eaves, and complex curved geometry. Despite only using 7.6 tons of steel, the roof structure achieves high structural performance, demonstrating the efficiency of light steel framing in demand applications. A defining technical challenge of the project was the roof drainage strategy and the cantilevered eaves on a curve. The architectural requirement for a continuous, visually clean roof edge resulted in a roof design necessitating a continuous concealed box gutter and an internal drainage system. Once again, this configuration required the ultraspan structure to be precisely engineered to accommodate the internal drainage zones. These were in the form of subframes that were assembled on-site and meticulously aligned to accommodate the curved perimeter and cantilever lengths, achieving a smooth and uninterrupted ceiling plane across the full extent of the roof overhangs. The result is a refined roof structure that demonstrates steel's role as a critical enabler of both functional, performance, and architectural expression within a commercial retail environment. The ultraspan roof cost on this entire project was only 1.4 million rand. Truss depths were shallow and relative to the span, reinforcing the efficiency of the ultraspan system. The structure consists of trusses supported on reinforced concrete beams. Deep cantilevered eaves generate uplift forces, which were resolved through engineered tie-downs and lattice girder actions at hip corners. Efficiency was achieved at approximately 11.8 kilograms per square meter, significantly lighter than conventional systems of similar complexity. Initially, the roof was architecturally designed for timber roof, but given the complexities of the shallow height, 1.25 meters, and the long span, 18.6 meters, including the 4-meter cantilevers around all eaves, rendered a timber structure not feasible for the complexity of the roof. The precision ultraspan system was the perfect platform to achieve cladding accuracy and the architectural design intent. The ability to adjust the soffit members on the curve within the frame structure made for easy installation of the cladding. The cladding itself, from the main contractor being Top Hat Roofing, involved the soffit cladding and the roof covering to a value of 900,000 rand. This was completed at the end of March 2025. The structural engineers were MGD Consulting Engineers on this project. The cantilevered eaves detail had to flow uninterrupted around the entire building perimeter, including curved corners, demanding tight control of geometry levels and tolerances. A separate adjustable steel subframe was designed on the Mitek Premier system using the UltraSpan light frame system and designed to go beneath the cantilevered eaves to support soffits and cladding, allowing fine on-site adjustment to achieve consistent alignment and a smooth architectural finish. The 4-meter cantilevered eaves generated significant uplift and reaction forces at the support points. These forces required purpose-designed steel tie-down connections consisting of engineered steel plates and anchor systems fixed into the reinforced concrete support beams. At hip and curved corners, reinforced truss lattice girder action was introduced with the roof space to maintain stiffness and control deflection while supporting the extended cantilevers, demonstrated in the diagrams to follow. Complex connections at the cantilever support and hip zones were engineered, detailed, and prefabricated, ensuring reliable load transfer into the concrete structure. The lightweight prefabricated pre-cut UltraSpan system enabled the design of load-bearing brackets manufacturing, ensured transport in manageable sections, on-site assembly without cranes, and adjustability during erection, which was critical in achieving the curved geometry and tight soffit tolerances. Mitek utilized its in-house Mitek 3D design platform to develop and communicate the UltraSpan roof solution. The digital model allowed early visualization of the long span trusses, cantilevered eaves, curved geometry, and integrated box gutter system, and this was shared with the project team for coordinated review. This facilitated early confirmation of roof form, cantilever extents, and soffit alignment prior to fabrication. It reduced approval cycles and ensured alignment between structural performance and architectural intent. At this point, I would like to request the members of the judging panel to take out your phones and scan the QR code that's on your screen. It is a shared 3D model that was used to confirm the roof form, cantilever extent, soffit alignment, and service routes. The model was reviewed by the architect and engineer in their own platforms, ensuring constructability before fabrication. Both professionals commented that being able to view the service routes enabled them to foresee that there were no challenges when it came to installation on site. It avoided rework and late changes on site. The coordinated 3D model improved communication between all disciplines and supported accurate detailing of complex connections and provided a clear reference for fabrication and erection, contributing to efficient site execution. The metal cladding or roofing in the space of the project that we have put forward, the manufacturers were Ivocore and Global Roofing Solutions. The product was the IBR roof sheeting and clip-tight sheeting, and the roofing contractor was Top Hat Roofing. The cladding system includes concealed fixed roofing sheeting, IBR wall cladding, and aluminum composite soffits. The challenge was maintaining consistent soffit levels around corners while integrating the box gutter. This was the challenge that the roofing contractor had called out. However, he said it was achieved through a secondary adjustable steel subframe provided by the UltraSpan design system tied directly into the roof structure. Key interface challenges included coordination between roof sheeting, box gutter, and soffit returns, maintaining consistent soffit levels around the curved corners, managing the inward sloping roof folds and internal drainage. And these challenges were resolved through the close coordination between the structural framing and cladding detailing, supported by the digital model Mitek 3D platform and on-site adjustment of the secondary steel framing provided by the UltraSpan system. Lightweight cladding materials reduced imposed loads on the structure. Durable, low-maintenance finishes support long-term performance. Prefabricated steel subframes minimized waste and improved installation efficiency. Ultraspan ensured that the complex roof geometry could be assembled accurately on site with minimal adjustment. All Ultraspan components manufactured at Mitec's Midrand facility, cut to length, pre-labeled and bundled for erection sequence. This ensured traceability and reduced site handling and errors. Bolted connections supported accurate installation and adjustability. Technical excellence was achieved through precision roll forming and cut-to-length manufacture of all members, manufacture of purpose-designed components for cantilever support and connection zones were consistent. Dimensional control across varying member lengths and geometries was also consistent. Following fabrication, members were bundled at the Midrand facility according to the erection sequence and packaged for transport. This logistic strategy simplified the on-site handling, improved installation efficiency, and reduced double handling and material waste. The result? A smooth transition from factory fabrication to site installation. Despite long spans and deep cantilevers, the roof was erected without cranes. Scaffolding and controlled manual handling were used, supported by the lightweight nature of the system. No late-stage design changes were required, and alignment was achieved progressively. Challenges were managed through factory-prepared, pre-labeled components matched to site drawings, bundled delivery aligned to erection sequence, close coordination between the steel contractor, fabricator, and engineer, on-site adjustability inherent in the Ultraspan light gauge system made for ease of application. According to the roofing contractor, the core challenge was supporting a shaped cantilever that also housed a concealed gutter, including at hip corners. This was resolved through adjustable subframes and embedded lattice girder elements tied back to the primary structure. The core challenge was supporting a shaped cantilever that also concealed the gutter. Disruption to surrounding stakeholders was minimized through efficient sequencing and reduced on-site fabrication. The absence of large cranes and heavy lifting operations further reduced site congestion and safety risk. No late-stage design alterations were required. Minor site clarifications arose. When those arose, they were resolved without compromising quality through coordination with the design team and reference to the approved 3D model and drawings. Steel enabled long spans, precision detailing, concealed drainage, and efficient construction, all within a fast-paced retail environment. Alternative materials would have struggled to deliver the same balance of accuracy, adaptability, and constructability. Steel was fundamental to the success of this project, enabling long spans, deep cantilevered eaves, and integrated concealed drainage to be achieved efficiently and accurately. The Ultraspan steel roof system provided the precision required to accommodate curved roofed edges and tight soffit tolerances, whilst it still remained adaptable during installation. Mitec ensured quality on the fabrication side of this project through ISO certified systems, Mitec site drawings, blue tech screws for visual inspection, and inspections by a Mitec appointed engineer. Factory fabrication reduced waste and improved consistency. Ultraspan components were cut to length, inspected, pre-labeled to approved Mitec site drawings, and bundled according to erection. It was consistent across the professional team, from the engineer to the architect to the roofing contractor, inclusive of Mitec, that beyond technical merit, what makes this project a winning project is the seamless integration between design fabrication and installation, supported by factory controlled production, clear site documentation, and disciplined quality assurance. This project demonstrates how steel can deliver precision, efficiency, and architectural clarity in an application where simplicity is often expected. The project team collaboration was achieved through close collaboration between the architect, engineer, fabricator, and contractor. Early coordination, shared digital models, and ongoing technical engagement enabled challenges to be resolved proactively, ensuring quality was maintained throughout the project lifecycle. What we're most proud of is how the architectural intent, engineering, fabrication, and installation align. This project demonstrates what steel can achieve when collaboration is genuine and disciplined. Thank you.